Good day everyone, my name is Graphics. Today we'll be looking at an aspect of R&A which is called vapor compression system, and the question goes like this. In a refrigerator, R134A is compressed isentropically from a saturated state of -5 degrees Celsius to a pressure of 11.6 bar. The refrigerant is then cooled at a constant pressure up to 25 degrees Celsius, and the refrigerant is then throttled down to a temperature of -5 degrees Celsius, at which it is evaporated. Determine the temperature and enthalpy after compression and the coefficient of performance COP. Take constant pressure to be equal to 1.175 kJ per watt kilogram Kelvin. Now, I would like to take you down the memory lane to remind you about some things. Now, this is a vapor compression system. And in a vapor compression system, we have 4 components, which is the compressor, the condenser, the expander, and what? The evaporator, right? Which is this. Now, this is the compressor. There's always a work input into the compressor, right? Now, this is the condenser, where heat is rejected. This is the expander, but in this case we have replaced it with a throttle valve, right? Now, this is the evaporator, where heat is absorbed. So we have state 1, state 2, state 3, state 4, right? Here there's a work output. Here there's a heat is being absorbed by the refrigerant Q4 to 1. Here there's a heat rejected, and that will be Q2 to 3. Are we good? Now, what you need to understand, I'm using this as a guideline to explain this question here. Now, one thing you need to know here is this. We have what is called the TS diagram for this, and this is the T here. I will have what? The S here. I will have our dome this way, right? Now, one thing you need to understand is that if I divide this into 2 this way, the left hand side is said to be my gaseous region, and the right hand side is said to be my gaseous region. The left hand side is said to be my liquid region. So instead of me using L, I will use F to represent liquid. While in between is said to be my liquid and gas, so I'll be using F and G. It's also called the wet region. Anything that falls on this line is said to be what? Saturated. Is that taken? Now, from this point here, our dryness fraction X is equals to 1. It means there is no gas, there is no liquid at this right part of it here. There's no liquid here. But at this part here, my dryness fraction, at this line here, from here to here, my dryness fraction is equals to what? 0. Because from here to here we have saturated liquid, From here to here we have saturated gas. So from this point to this point, saturated gas. From this point to this point, saturated liquid. Is that taken? Now you need to understand something here, that anything that is outside this region here, somewhere around here or this part, is said to be what? Superheated. And anything outside this region here is said to be what? Subcool. Now let's move forward. The question now says, in a refrigerator, R134A is compressed. Now the refrigerant used is R134A. So our refrigerant, which is the working fluid, is giving us R134A. Now we move forward. It's compressed isotropically from a saturated state of -5. Now you see 1 and 4 is at the evaporator, and the evaporator, what happened, that is where heat is being absorbed. Is that taken? At the condenser, that is where heat is being rejected. So it's at the saturated state. What saturated state is at state 1. So at this point here, let's say saturated, since it's falling on this line, and whatever enters the compressor is a gas, right? Liquid will not enter the compressor because this is a reverse Carnot cycle, which is a vapor compression cycle. So at this point here, what is entering into this compressor as state 1 is the gas. So, and it says it's saturated, so it will fall on this line here. So we'll call it 0.1. And it is initially at low temperature T. So that is what we call it T1. We call it T1 equals to what? -5 degrees Celsius. Right? So the next thing we'll do here, it says to a pressure of 11.6 bar. Now we need to convert that pressure into temperature, and we're going to use our steam table. So when you compress, you know that when the gas, the vapor at low temperature and pressure enters the compressor, the compressor increases the pressure and the temperature to state 2, right? So we're talking about T2. So as it has increased the pressure and temperature to state 2, so it's moving straight up here, right? Somewhere around here. Let's call this point here state 2, because when the vapor enters, the pressure and temperature of it will be increased towards state 2. That means it will be what? Superheated. Because the question is make us understand that to a pressure of 11.6 bar. Now this state 2. From here, if we want to convert our pressure into temperature, because this is a TS diagram here. Now our pressure, we'll put it this way, that it is P2, because when you have compressed it, it will move to state 2. So we're talking about pressure 2. So our pressure 2 here is equals to what? 11.6 bar, right? So that means our temperature 2 will be P2. Our T will be P2 at what? At P2 at 11.6 bar, right? So we're going to check on our steam table to know what temperature T2 is. Now this is what we'll do. On our temperature table, our steam table, we are going to look for the pressure at 11, because this is the temperature column, pressure column, and the specific volume column, and so on and so forth. We are going to look for 11.6 bar on this temperature column, this pressure column here. And we'll move forward. This is 11.59, so that approximately 11.6 bar. So the temperature at 11.6 bar here is what? 45 degrees Celsius. So I'm going to write it down. So this will give me 45 degrees Celsius, right? So what I'll do is that after it has been compressed, what happened? It enters the condenser. So it will come down here and it enters the condenser. So it's set to a pressure of what? 11.6 bar, right? Then that means from here to here, this is from 2 to here is the entry of the what? The condenser, and this is the condenser here. The condenser is here, the evaporator is here. So the evaporator at this point, we know that our evaporator at this point is minus 5 degrees Celsius. Then the condenser here is what we just got now, which is what? 45 degrees Celsius. So it's entering from 2. It needs to come down here and enter into what? The condenser. Are we good? So it's going towards this direction. It's going towards this direction. So from here to here is the condenser. To what? Now, so the refrigerant is then cooled at the constant pressure of what? 25 degrees Celsius. So it's now cooled again. So that cooled is subcool. This place is then cooled here. So this is our T, I'll call it T3, equals to what? 45 degrees Celsius. Then when it's now cooled again, they first of all cool it a little bit. They call it the subcool, TS. So at this point here, it was cooled back down to what? 25 degrees Celsius. So our TS is equal to what? 25 degrees Celsius. Are we good? So I'll call here 1, 2, and I'll call this point 3. Then I'll call here to be 4, right? Point 4. Call it to be 0.5. Start taking. Now, if you look at this question here again, it's now said the refrigerant is then throttled down to a temperature of minus 5 degrees at which it evaporated. So I told you this minus 5 is the evaporated region, right? Which is the evaporator. So it's now throttled down to that point here. It's throttled down to reduce further to this point here. Are we good? So I'll call that point 0.6. So and 0.7. So after that, we are told to look for what? We should look for determine the temperature and the enthalpy after compression and the COP, right? So you see after compression. Now, as state 1 is before compression, because this is where it is entering into the word compression. As state 2 is after compression. So T2, we are looking for the temperature we'll be looking for will be T2, and the enthalpy we'll be looking for will be H2, right? So, and our COP, we just look for our what? COP also. So now let's start and see how it goes. So first of all, we need to know at this point here, we know that what? Entropy at state 1 is equal to what? Entropy at what? At state 2. That is one thing you need to understand. So calculating for the enthalpy and entropy of each point here. So that's all right. So at the enthalpy at state 1, we'll look for that. The enthalpy at state 2, we'll look for that. The enthalpy at state 3, we'll look for that, right? But we cannot really look for that also. So we also come to enthalpy, that is H4 at state 4. Enthalpy at state 4. We'll look for enthalpy at state 5 also, that is H5, right? We'll look for H6, right? And we'll look for what? H7. So are the things we'll be looking for, H7 too. Let's move upward. H7. So that is 1. So to look for H1, this is what you do here. Anything that is touching the saturated point of this touching the saturated line, or saturated line, or this line here, can be seen in the steam table. So we can see H1, we can see H3, we can see H4, we can see H5, and we can see H7 in the steam table. So let's start. So H1, since on the steam table, and I told you at the left hand side, at the right hand side, everything around this side is what? Is a gas. So it will be what? Hg. So if you trace H1, the temperature is what? -5. So it will be Hg at what? At -5 degrees Celsius. So I'll go and check on my steam table and look for Hg at -5 degrees Celsius. Now if you look at it very well, we'll take this is temperature bar, pressure bar, specific volume bar. This is enthalpy HF bar. This is enthalpy Hg bar. So go and check -5. I'll go and check on that point. So this is -5 and this is Hg here. Can you see? This is where they meet at this point here. So Hg coming down and is meeting -5 here. So it is what? 395.49 kilojoule per kilogram. So we have, which is equals to 395.49 kilojoule per what? Kilogram. Now the next thing we'll look for will be what? H2. We can't look for H2 because we're looking for H2 here, and apart from that, H2 doesn't fall on this saturated line, so we cannot look for it. So the next point will be H3, right? So look for H3. We'll look for H3. So H3 at, this is H3 here, right? So it's at what? 45 degrees Celsius, and it's at the right hand side at this region. Now I divided it into 2. So this side will say to be what? Gas. So it will be Hg. H3 will be Hg. H3 will be Hg at 45 degrees Celsius, and that will give me, if you check on your steam table, so check for 45 degree, and this is what? 45 degree here. So look for, we'll trace it, and this is, we're having this guy here, 421.53 on the same Hg here. Can you see the Hg column? 421.53. So I'll go and write it, 421.53. So we have 421.53 kilojoule per kilogram. Now the next thing we're looking for will be H4, because H4 is also touching the saturated line, right? So our H4 will be, we'll check H4, but what do you notice? The H4 is falling at the left hand side on the liquid region, so it will be HF now. So for H4 we are going to be having HF at 45 degrees Celsius, because it's on the temperature here is what? 45. We are looking at, it falls at the left hand side. So, and that will give us what? If you check your steam table, you go and check for HF, this HF here, and this is temperature, you go to 45, and this 45 here, right? So you look for HF. So HF is this, that is 263. Because if you look at it, if you trace it up, this H, the column of HF, and this is what? 45, and this is 263.92. So to be 263.92 kilojoule per what? Kilogram. That is my HF. H4. Okay, the next one I'll check that is touching it is what? My H5, right? So the H5 is also falling at the left hand side, and that will be what? HF at, now H5 is on what? 25 degrees Celsius. So we're having 25 degrees Celsius equals to, you check it on the steam table, and when you check it, we're having this. So you go and check for 25 degrees Celsius here, this 25 degree, and you go and check for what? HF, and that is what? This is what we're having here, 234.52, right? 234.52 kilojoule per watt kilogram. Then the next thing we'll be checking again, we can't check for H6 because it's not falling on the column, and we can still check for H7 if we want to. So it will be HF. We can check for H7 too. So my H7 will be HF at minus, let me put it there, H7 will be HF at minus 5 degrees Celsius. So we'll be having 193.32 kilojoule per kilogram. Now, I haven't solved then H6. We can't look for H6 because it's not falling on the saturated line here. So we'll now move forward. After calculating for the enthalpy, then we'll go for what? Entropy also, right? So entropy is always represented using X. So just like we've done here, we'll look for what? For X1, since we have H1, automatically we have what? S1. And S1 will also be what? SG, right? Because anything 1 falls on the right hand side. So the same temperature, SG at what? Minus 5 degrees Celsius. So let's check on our steam table. So you go on, this is enthalpy here, and this is entropy. This is SF, that's for liquid, this is SG for gas. So check for minus 5. So this minus 5 here, right? So this is where it's moving, it's meeting it at this point here. So we're having 1.7294 kilojoule per kilogram Kelvin. 1.7294 kilojoule per kilogram Kelvin. That is for what? X1. Now you go for the next one, which is what? We have, since we have H2, we look for S2 too. But since there's no S2 on the saturated line, so since there's no H2, there can be S2. So we need to calculate for S2 also. Now we have S3, because it's also falling on the saturated line. So it will be, since it's HG here, so here will be what? SG at what? 45 degrees Celsius. So if you check it on your steam table, we are going to be having 1.7072 kilojoule per watt kilogram Kelvin. Is that taken? Now the next thing we're looking for, since we have H4, we're having S4 also. So look for our S4. So S4 will be SF at 45 degrees Celsius, because this is SHF, so this will be what? SF, because they are both on the same point. So at 45 degrees Celsius. So we are going to check on our steam table. SF at 45 degrees Celsius. So if you check for SF at 45 degrees Celsius, we'll come here. This is 45 here, right? So we check for SF. SF is this. We're having this 45. So this is it here. 1.2138 kilojoule per kilogram Kelvin. So we have 1.2128 kilojoule per kilogram Kelvin. So you can also look for S7 too. So S7 will be equals to X7, will be equals to what? SF, since this H7 is HF, so this will be SF at minus 5 degrees Celsius, and we're going to be having 0.9754 kilojoule per kilogram Kelvin. So we've solved all this out. That's the first thing. You bring all of them out. Now we are looking for what? We want to look for H2, since we don't calculate H2. So how can you calculate your H2? Is this way. But before we calculate our H2, the question says we should look for what? Look for temperature first, right? look at the question here. It says determine the temperature, and the temperature determined is what? T2. So let's look for T2. So for us to get T2, we need to remember this relationship that says that we'll write it out and say recall. Let me say calculating for T2, calculating for what? For T2. Then you write recall. There's a formula that says that what? S1 is equals to what? X3 plus Cp, the log of what? T2 over what? T3. So that is the relationship we are going to be using. So I'll call it, let me just call it equation 1, right? So we need to know what S1 is. We need to know what S3 is, but we know very well that our Cp given in equation is 1.175 kilojoule per kilogram Kelvin. It is given in the question. If you check the question here, so we have what? Cp to be given as what? 1.175 kilojoule per kilogram Kelvin. So move forward. So from here, we'll start putting our value. Now what S1? We calculated for S1 to be 1.7294. So this is 1.7294. Calculated for S1 here. If you look at it, this is our S1 here, right? So equals to the X3 here is given to be 1.7072. 1.7072 plus the Cp here is what? 1.175, then log of what? We don't know what T2 is, which is what we're looking for, all over T3. Now what is the T3? T3 is given to be this. T3 is this, right? That's our T3 here. T3 is given to be what? 45 degrees Celsius. But now you're not going to use it in Celsius, you need to convert it to Kelvin, right? So T3 equals to what? 45 degrees Celsius, which is equals to 273 plus 45, and that will give us what? 318 Kelvin. So that's what we'll be using here. So we'll place our 318 here, right? So let's start. Now, so moving forward here. At this point, I'll take this to this point. So I'll be having 1.7294 minus 1.7072, because when this guy is coming here, become a negative, equals to what? 1.175 log T2 over what? 318. So we subtract this. And when you subtract these two here, you're going to be having this. Video. So we have 1.0191 Brian don't come on equals to T2 over 318. So
I don't post anything down. Right call left.
So
No.
now 3. You're going to be having times 1.175. So this will give us 380 here, 380.779. So H2 here will now be plus 421.53. So will give me 802.309 kilojoule per kilogram this thing. So this is what we're having here, right? That's the enthalpy H2. Now we search forward. The next thing we'll calculate for will be our COP, coefficient of performance. So we know that now the next thing is calculating for COP, coefficient of performance. And the coefficient of performance COP is equal to what? The desired effect all over what? The work done. So the work done, right? So from here, what are desired effect? Desired effect to be, if you look at this point here, we have our cooling comes from at the evaporator here, right? So and the evaporator is at this point here. Is that taken? So our desired effect will be H2 minus H1 at the compressor. As we have this, desired effect is H1 minus H6, right? H1 minus H6. Can you look at it? H1 minus H6 divided by the work done. What does the work here is the compressor H2 minus H1. So we're having H2 minus what? H1. Is that taken? So at this point here, what's our H1? Our H1 is giving us 395.49. We have 395.49 minus the H6. H6 given here is equals to, the H6 is equals to what? The H5. So H6 here is equals to what? H5. So what's our H5? Our H5 giving us what? 234.52. So we have 234.52 all over H2. What is the H2? H2 is what we just got here. This is our H2 here, which is 802.309. We have 802.309 minus H1. H1 is given to be 395.49. We have 395.49. So by the time you do that, we'll be having this. So 395.49. Let me see. 395.49 minus 234.52, and we have 160.97 all over 802.309 minus 395.49. That'll give me 406.81. So our COP, coefficient of performance, will now give me 160.97 divided by 406.81, and that'll give me 0.396. So this is our calculator. So therefore the T2 is equals to 324.07 Kelvin. The H2 is equals to 802.309 kilojoule per kilogram, and the COP is equals to 0.396. So thank you for watching. We'll meet in our next video. So if you find this very interesting and very useful to you, please don't forget to click on the subscribe button. Bye.